all. I welcome all the participants to the day 2 session. I, Chaitanya, Teacher Assistant Professor, Department of Electronics and Communication Engineering, would like to take this opportunity to introduce today's resource person, Dr. Ajish Abraham, who has graciously accepted our invitation to join us today. Dr. Ajish Abraham is a professor of electronics and acoustics at Mysore. He has completed his PhD in electronics from the University of Mysore and postdoctoral training at the University of California, USA. He has 36 years of teaching as well as research experience, 10 years at Central Scientific Instrument Organization, Chandigarh, followed by 21 years at All India Institute of Speech and Hearing, Mysore. His current research project includes development of robot for articulatory simulation, development of an automatic speech processing system for assessment of stuttering, automation of Malayalam articulation test for assessment of articulation, etc. His work has involved developing automated diagnostic system for severity assessment of speech disorders. He has been involved in developing assistive technology devices for the rehabilitations of persons with communication disorders. He has published several papers in reputed journals. His areas of interest includes design and development of biomedical equipment, audio and speech processing, hearing aid technology research, acoustic noise, etc. We are honored to have you with us today, sir, to share your knowledge. Thank you.
Part of this faculty development program. So I think you started with A and signal processing yesterday. So today morning I'm taking you to a slightly different topic. It's an application of signal processing. And this application is for hearing. So, I think you must have seen people who use hearing. So when you see them, you may be thinking that it's just a small amplifier which enhances the loudness of sounds and feeds into your ears. That's generally people think like that. But it's a very complex processor. The reason for that being a complex processor is because of the signal processing which is required to process the sounds and make it audible. So in today's presentation, I'll be going through, I'll be giving you an overview of the signal processing strategies which are involved in the hearing aids. And under three major heads: one in channel separation, in dynamic range compression, then noise reduction. And then I'll give you some insights about the gaps in hearing aid technology which you can take up as the research problems to work on. So starting with the word hearing impairment. It is the inability of an individual to hear outer ear, middle ear, and inner ear. So this inability to hear properly, it may be because of the improper development which happens by birth, damage which can happen to any one of us, or disease to any part of the hearing mechanism. So here you may be thinking that we are all with good ears now, and it will remain like that forever. Don't ever think like that. Just last month, in the month of November, we got a young lady which is known to me. She is of 25 years. She works in Bangalore. Her parents are in Bangalore. So one day morning, suddenly she called me and told me that, sir, I'm not hearing anything on my right ear. So then I asked whether you had any viral fever in the last 2-3 days. She said yes. And I told her immediately you take any transport available and come to ICU or HDQ. So basically what happens is when we have viral fevers or any kind of viral attack, we take it very lightly. We do our own treatment with paracetamol and all. But this virus can severely impact the hearing mechanism. So when the virus attacks the hearing mechanism, the perfect ear can go down within 24 hours. The only remedy to overcome that is by giving an injection directly to the tympanic membrane, which has to be done within 48 hours. If it is done within 48 hours, the hearing can be recovered. The more it becomes late, the more it becomes difficult. So luckily, she was in that 48 hours span. She came here to do this injection. She has to be taken to a minor OT with some procedures. Injection was given, and 80% of her hearing got recovered. So this can come to each one of us anytime. So be very careful about that. So any problem in the outer ear, middle ear, inner ear can lead to hearing impairment. So if we divide the types of hearing losses, there are different types of hearing losses. The first one is called conductive hearing loss, which happens in 10% of the cases. The incidence is only 10% of the cases, where the disorder is either in the outer ear or middle ear. The causes for this infections of ear canal or middle ear, fluid in the middle ear, perforated tympanic membrane, or dislocation of the ossicles. So in the middle ear, we have 3 bones here. Ear. So these 3 bones, which we call as malleus indus stapes, these 3 bones, if they are damaged, then or dislocated, it can lead to conductive hearing loss. And the symptoms for this are soft sounds. Soft sounds means sounds of lower amplitude, lower loudness, like murmuring sound. They will not become audible. And very high sounds, very intense sounds, you will feel that you are hearing it as a normal sound. The second type of hearing loss, which happens in 90% of the cases, is the sensory neural hearing loss, which in short form it is called SN hearing loss. And this happens in the cochlea, in the inner ear, or when the auditory nerve is affected. So the causes for this is age. So as we reach age, when we cross 60s and 70s, this happens. This is because of the problems in the cochlea. Then exposure to loud noise. So that's why noise pollution is becoming very significant nowadays. Exposure to loud noise can damage the cells in the cochlea and can lead to this. Then the viral infections. I was mentioning about the viral infection. So this can also lead to this. And genetic problems like by birth, it can happen. So here, it's slightly different from the earlier case. Here, it's difficult to hear the soft sounds, the low loudness sounds, whereas the intense sounds can be heard. So normally, when we talk to old people at our home or at door, they'll ask us to speak loudly, or only when we speak loudly they can hear. That's because the loud sounds they can hear, whereas the soft sounds they cannot Another type of hearing loss is the mixed one, where you have both conjunctive and sensory neural hearing loss, and this can happen either because of the outer ear or middle ear or inner ear problems. And another very rare type of hearing disorder is called central auditory processing disorder (CAPD). This is because of the problems in the nervous system, the central nervous system. So this can happen with people with mental retardation, where the brain cells are not developed. It can happen when you get stroke, or when you damage your brain due to some accident. So tumors, lesion caused by stroke, and other changes in the neural structure can lead to this. So the symptom for this is poor word recognition. So when we speak a word, you hear that word, you comprehend that word and respond to that. So they may not be able to hear that word properly. So when I say something like, if I say cashew, they will be hearing it as some other word. Okay? So that is a typical symptom of this type of hearing loss. So now we learned about the 4 different types of hearing losses: conjunctive hearing loss, sensory neural hearing loss, the mixed hearing loss, and central auditory processing hearing loss. So when such kind of problems happen, we feel that we are not hearing comfortably, or we are hearing only very loud sounds, or we cannot hear soft sounds. So that time what we have to do is we have to go for assessment. So there are 4 different ways of, or 4 different tests, prominent tests which are done for hearing assessment. The basic one is the audiometry. The second one, which is on the right side, that tests the middle ear functions, which is called tympanometry. The third one, which is here, this is called auditory brainstem response, where electrodes are placed on the head and the response is collected and analyzed. And the last one is called autoacoustic emission response. So this doesn't mean that all the 4 tests are done when you have problems. Depending on the type of problem, the tests are done. Depending on the age of the person, the tests are done. So the audiometry test we call it as a subjective test. Because the instrument, what it does is it presents a stimulus to the ears, and it is the subject who should respond, whether you are hearing that tone or not. So to do this test, we require a subjective response. So imagine this small child, if the hearing has to be tested for this small child. This test is not possible because the child cannot respond, child cannot say that I am hearing the sound. So for such cases, we will do this test, which is called auditory brainstem response test, or ABR test. The right corner one is done, it can be done within 12 hours a baby is born. As soon as the baby is born, whether the baby has got hearing problem or not, that can be done with that test, which is called autoacoustic emission test. So in most of the Western countries, the mother will not be discharged from the hospital unless this test is done. Okay. It cannot be implemented here because that instrument is very costly, it costs 6 to 8 lakhs. Many of our primary health care centers doesn't have that facility, so that's why it is not made mandatory here. But nowadays, in almost all of the district hospitals, this facility is there. Most of the established private nursing homes, this facility is there. It will test whether the baby has got hearing problem right at the time of the birth. The corner one, which is called middle ear analysis, so when we went through the process for the conductive hearing loss, that it can be because of the problems in the middle ear. So what that instrument does is it checks the impedance of the middle ear and then decides whether the middle ear is functioning properly or not. So the audiometric evaluation is the basic test. Has anybody in this group undergone this test? The hearing test? You have undergone. So basically, this is conducted in a soundproof room. Soundproof room means the room which is isolated from all the external sounds, and that is the device. And this is the situation. It has got 2 rooms. It's almost like a studio setup where the instrument and the tester will be controlled, will be sitting in the other room, and if you are undertaking the test, you will be in the opposite room. Okay. So from here, tones are presented, tones of different frequencies are presented from 250 Hertz to 8000 Hertz, different tones are presented. And the intensity at which you hear the tone is marked here. So for example, this is the frequency axis, this is at 250 Hertz. So when the tone is presented, if your hearing was normal, you should have heard it at this level, somewhere between 0 and 2. Okay. Now this person is an actual audiogram where he is hearing at 75 dB. So he needs 55 dB more loud sound to hear like this, to hear like a normal person. So like that, for each frequency, the level at which his hearing is marked, that is for the right ear and left ear separately. So now by looking at this, we can find that his hearing level is not normal. If the hearing level was normal, this whole curve would have been in this block of 0 to 20 dB. So this much of loss is there. So this is this amount, this 75 minus 20 dB, 55 dB is the hearing loss. So now after detecting the hearing loss, the hearing aid comes into the picture. Now to compensate for this much of loss, you have to increase the loudness by that level. But you see here, the loudness enhancement required is different for different frequencies. Okay? And that makes the hearing aid processing a little complex. So now, when we think about the human ear, the human ear does several other functions other than hearing. These are called add-on functions. Okay? So the thing which is an add-on function which the human ear does is the speaker identification or the object identification. So nowadays we are communicating through mobiles. The numbers are fed with their names. When the call comes, we know who is calling. But in earlier days we had the line phones where there was no such facility to feel. But even at that time, when some person who is known to us, when he calls, maybe a relative or our friends, without introducing him, we can identify him. Just by hearing the voice, we can identify him. That is speaker identification, which the ear does automatically along with the process of hearing. The second thing is listening to desired sound emits noise. Okay? So when we travel, we have to travel to bus stands, railway stations, airports. They are very noisy places. Or when we go to market to purchase something, they are very noisy places. Even amidst all that background noise, we can clearly hear what the person whom we are talking to tells us. Even though the outside noise is much higher than our talking noise, we can easily hear that. So that is another add-on feature of the human ear. It focuses to the source of sound which you want to hear. The third one is sound localization. Okay? So all of you are sitting here right now. If I go to the last row and drop something there, what would be your immediate reaction? All of you will turn back. Okay? That is because along with the process of hearing, you are able to localize the sound, the locality from which the sound is originating. This is called localization. This the human ear does with a beautiful calculation of something called as interaural time difference. So that's why we have 2 years. People think that 2 years have been given one as a standard, not that. Because we have 2 years, we are able to localize the sound. Okay? So I'm sitting here, the sound happens, suppose the source of sound is here. It reaches both my ears. But there will be a time difference between the sound which I am hearing through this ear and this ear, because this ear is far from the sound source. And just by calculating that time difference, the ear identifies, or the brain identifies from which side the sound has come. So this is another property which the human ear has. Next one is pitch perception. So those who have learned music or those who are familiar with music know about the pitches. Okay, so at least we will come to know that whether the sound is low pitch or high pitch, because we have that sensation in our brain. So that pitch perception is another add-on feature which you get from this. Next one is music perception. Okay, so if I tell you, all of you, to close your eyes, and if I play some musical instrument here, just by hearing the sound, you will be able to tell me whether it is a guitar or a keyboard or a veena or a violin. Right? That is music perception. You are able to perceive and differentiate the sounds from different musical instruments. That is also an add-on feature which the human has. Then the speech perception. So now I'm talking to you, you are hearing me, you are comprehending what I am conveying to you. Okay? Suppose I talk in a different language which is not known to anyone of you. You will be able to hear me, but you will not be able to understand a single word which I say. Okay? That property is called speech perception. You are able to hear and then perceive or comprehend what I am trying to convey. That is also an add-on feature of the human ear. So if the human ear doesn't work properly, all these features will get affected. Or in other words, all these features are achieved when sounds are processed by human ear and the brain. Okay, so we talked about the different types of hearing losses, and when the human ear performs badly or in a different way compared to a normal ear, all these features will get affected. It is not only the hearing, ear listening to desired sound will get affected, the speaker identification will get affected, the localization will get affected. That's why you must have noticed when you talk to old people, they fail to identify from which side the sound has come. If you are calling from here, they look somewhere else because their localization is affected. Okay? So all these features will get affected when you have this. So what I am trying to say is that the hearing impairment will lead to deterioration of all these features. Reduced ability to separate desired sound from undesired sound, inability to use the fine structure cues which helps us in pitch and music perception, reduced hearing sensitivity, all these effects. So when we are compensating for hearing loss with the hearing aid, not only we have to compensate the audibility or loudness, we have to compensate for all these features. Okay, we have to compensate for the localization, we have to compensate for listening among noise, we have to compensate for speaker identification. That is why the hearing aid signal processing is complex. Okay? It's not only increasing the loudness will not help you in compensating the problem in these add-on functions which the. So what we expect from hearing aid is that it should enhance the signal. That's the first duty of hearing aid. Signal processing. First objective of hearing aid signal processing. Adaptive noise reduction. So when we are in a noisy place, the noise should be reduced so that we can hear the speech from the person whom it is said here. Then cleaner sound. Cleaner sound means the sound should be free of noise. Then better shaping of the frequency response. So when we saw the hearing loss at different frequencies, it was not a straight line, it was like this. Okay? So the frequency response of the human ear also has to be compensated by providing different gains at different frequencies. And then optimization of the microphone direction and quality. So the hearing aid signal processing has to do all these functions. That's why it is becoming complex. Now, when I go for presentations like this, after the presentation, at least one person from the audience will come and ask me these questions. Okay, we are having a very good processor in our hands, the mobiles, for which we have spent at least 15 to 20,000 rupees. It has got a very powerful processor. then why do you require a small processor here? Why can't all these processors? So these are simple processes as far as mobile is concerned. Because it can do much advanced processing. So why can't we use the mobile for processing all this? Okay, so we use earphones and listen from our mobile. In the same way, we can use earphones. Whatever processing is required, which I described, can be achieved in the mobile, and we can use that as okay. Why can't the mobile be used? Is there any answer from your side? Why can't our mobile phones be used as earphones?
Radiations.
Radiations. And
Frequency issue. The frequency parameter issue.
frequency parameter issue. And any other answer?
Delay in the perception. Delay in the
Yes, exactly. This is the absolutely right answer. The processing which happens in the mobile, it takes time because the mobile has to do other functions also. Basically, it's a communication device. So if we use it for this, it will not be able to devote full time for signal processing. Okay, so you have to do time division multiplexing. So then the processing time it takes to complete all these processes will be too long. And studies have shown that when you process the sound and feed into the ears, the delay should not be more than 8 milliseconds. Because when you are talking to a person, you are synchronizing with his lip movement also to understand the sounds. Okay? So if the sound which you hear is delayed by more than 8 milliseconds, it creates confusion. Okay, so that means all these processing which we have seen has to be completed within 8 milliseconds. This is not possible when you use it. So that's why a dedicated processor is required to do this job. Okay, so coming back to hearing aids, this is the most fundamental technology. So I will not say that the hearing aids can solve all the hearing loss issues. We have seen different types, different causes for that. But almost 80 to 90% of the hearing issues can be corrected with the hearing aid provided it has sensory hearing loss. For conductive hearing loss, it will not work, only for sensory neural hearing loss. So the primary function of the hearing aid processor or hearing aid signal processing is to process the acoustic stimuli such that the signal reaching the inner air cells, that is the inner ear, is as close to the signal that would be presented to the inner ear cells by a healthy auditory system. Okay? So the hearing aid sound, the output of the hearing aid should be very close to the natural speech. If it is not close to natural speech, again we will have listening problems. Okay. In addition to that, it should address the frequency dependent hearing loss. So we saw the curve which has got different hearing loss at different frequencies. So it should be able to address the frequency dependent hearing loss. So earlier, the whole thing was done by analog hearing aids, where we had the analog amplifiers, where none of these features other than the audibility feature was implemented. Now in 1996, the first hearing aid, digital hearing aid was launched, and after that, the entire hearing aid signal processing has been taken care by the DSPs. So nowadays it is very difficult to find a hearing aid without it. So basically, the structure of a hearing aid is like this. It will have either one microphone or two microphones, which receives the sound, then convert the electrical signal from the output of the microphone to digital form. Then comes the DSP, where the entire processing is done, then converted back to analog and given to the earphone. So this is the basic structure of a hearing aid signal processing system. So, and thus all the processing is done by this chip. So nowadays, the A to D, D to A are all integrated into the same chip. So what you see in hearing aid is just this microphone, a chip followed by the receiver or the earphone. So when we see the new developments in hearing aid technology, as artificial intelligence has captured many of our signal processing areas. So the same thing has happened here. The artificial intelligence and the health tracking features have come to hearing aids. The machine learning and processing based on machine learning has also been incorporated in hearing aids. And it is there with more features, remote care and apps like that. So nowadays, you can connect Bluetooth to the hearing aids, and you can connect your security devices also to hearing aids. So if you are out of home, if you have a CCTV camera at home, and if something happens there, the alarming signals you can hear through the through the hearing aids. So those features are also being implemented in hearing aids. Bluetooth and things. So these are all the latest developments in the hearing aid as per the paper published by Harrison B. in 2022. So the hearing aid technology, the focus of hearing aid technology nowadays is focused on 3-4 major areas. Just touch upon those areas so that it can lead to research problems which we can take up in the future. So the work currently going on in the hearing aid technology, one focus is on speech clarity. So many studies have shown that the clarity of sound which comes through the hearing aid is different from the natural sound. That means if you are hearing the speech directly and if you hear it through the hearing aid, there is some difference. Easily we can identify that this is natural sound and this is the sound which is coming from hearing aid. So improvement in the speech clarity has always been a desired feature of the hearing aid devices. Many surveys have been conducted from the hearing aid users. Some of the surveys are present here about how do you feel about the hearing aid or what is lacking in the hearing aid. Most of them reply saying that the sound through the hearing aid is different from natural sound. Now, when we think about our present day audio systems like our car music player or our TV system, we feel that the sound which is coming out through that is much better than the sound which we hear naturally. We would like to listen to those sounds than listening it naturally. So if that is the case, why this is happening in hearing aids? Why people complain that the clarity of speech is very poor? So studies are being done on that, and the advanced features which are now there on the hearing aid, they incorporate the narrow directionality. Narrow directionality means focusing to the desired sound as close as possible, echo adjustments and spatial configuration. So all these are done to improve the speech clarity. So what's going on in these areas, how to improve speech clarity by working in person. The next important research area which is going on in hearing aids is the background noise reduction. So in fact, that is how me and Patil sir we're trying to work together to find out some solutions for this. Now, when we say about background noise, it varies from situation to situation. And remember, for electronics engineers like us, noise, the moment you hear the word noise, the filter comes into our mind. Any noise, any electronic noise, electrical noise, we can eliminate with the help of filters, and the filter technology has gone very high with the advent of ESPs. But here the problem is, when you are trying to filter out electronic noise, you can easily do that because the noise is of a different spectrum or a different frequency range than the desired signal. When compared to the desired signal is in this range, noise is in a different range. Whereas here, the noise, the sound noise or the acoustic noise is in the same frequency range as the sounds which I want to listen. Okay? Suppose I am talking to sir now, and suddenly there is a break here, the classes have stopped, there will be a lot of background noise. The noise which are generated by the students, it is also speech, It comes in the same range of 250 hertz to 8 kilohertz. Then when I filter, what should I filter? Sir's voice is also in the same range, noise is also in the same range. So that is the biggest challenge which we face when we consider the noise in hearing. So that's why you must have noticed that clearly the word used here is reduction. It is not elimination. You cannot eliminate the noise at all. Only thing which you can do is reduce the noise to a lower level compared to the speech of sound. Okay? So for that there is a term called speech to noise ratio. Speech to noise ratio is the level of the speech minus the level of the noise in being. Okay? So it is said that if the speech to noise ratio is at least 5 dB, that means Sir's speech is higher to the noise level by 5 dB, I can listen to Sir's speech clearly. If I have normal hearing. But the person with impaired hearing, that difference, that speech to noise ratio has to be at least 15. Okay? So that is where the hearing aid signal processing research is work to reduce the noise level so that the speech to noise ratio is kept at level of 15. Okay? So all the noise reduction algorithms are focused on this. The next issue is the localization. Okay? So we have seen that the human ear automatically does the localization. So the moment you fit the hearing aid, the localization is lost because the interoral time difference with which the localization is done, that is lost because you are hearing through the hearing aids now, not the. So the interoral difference which the human ear automatically processes, that is stopped now. And the hearing aid has to do the processing. So by finding out the time of arrival of the sound at the microphones of the both hearing aids, time delay between that, then you have to find the interoral time difference and do the processing. Okay, so this can be achieved if the microphone which the hearing aid uses has got a 360-degree capture. Okay. So people are working on that to bring adaptive features into this using acoustic and motion sensors. So these sensors will help the brain to understand and process sound directionality. The last one is the automatic environment detection and adjustments. Okay. So now when we in our daily life we pass through different environments. Okay. So you have started your home. You must have come in a public transport where the environment is totally different. By environment I mean is the sound environment. So if you have come by train or bus, you are traveling through a noisy place with a different type of noise. If you are coming in your vehicle, then you face a different type of noise which is created by the traffic around you. Okay. If you are going to a market to purchase something, there it's a different type of noise. Okay. So all these we call as noise scenes. So these noise scenes are different for different environments. Now when I use a hearing aid, I have to travel through all these places. If I have to come for work, I have to travel. I have to travel either in my car or using a public transport. So if I use public transport, the processing which the hearing aid should do is different because there is it's a different type of noise. So if I'm using a hearing aid, what should I do is when I enter the bus, I have to switch on to one program. When I get down from the bus, I have to switch on to another program. When I'm taking the class, I have to switch on to another program. When I'm sitting in the department and talking with my colleagues, I have to use a different program. So these are required because the acoustic environment, the sound environment in these situations are different. Okay. Now if I do it manually, it becomes so irritating. Every time if I have to change that in the small device, it becomes difficult. So what is being done is the environment is detected automatically and then the processing programs are changed automatically. So that work is going on now. Modern hearing aids scan your surroundings 10,000 times in a second. Every second, 10,000 times scanning is done. In what environment you are. And according to the environment, the programs are switched inside the ASP. automatically adjust their programs to deliver an optimal natural sound experience based on any environment. Here, in fact, it is here the artificial intelligence comes in the picture. Okay, so you have to take the data from all these environments, and then using that data, you have to find out which environment you are, detect the environment, and then change the program accordingly. Another issue, another area of current work in hearing aids is own voice processing. Now, when you are using the hearing aid, you are hearing the other sounds through the hearing aid. Same way, you are hearing your own voice also through the hearing aid. You must have noticed this when you attend online programs using what is called Zoom or Google Meet. So when you wear the headphones and talk, you will hear your own speech also through the headphones, which becomes a little bit irritating. But since we all have a normal ear, the normal ear can clearly distinguish that and then process it separately. But when it comes to hearing aid, this own voice processing becomes difficult. So in fact, this is one of the problems which we are facing when we fit hearing aids to elderly people. They say that their own voice comes as a very loud voice to them because they all know what they are going to speak and they don't want to hear that voice very loudly. So when you adjust the hearing aid gain, you have to adjust it in such a way that the own voice has got very less gain because you don't require more gain for that. If you give more gain for that, that will be just a very loud sound, very brassing sound to your ears, which will be so irritating. Okay. So this is one area where work is going on. Identifying the own voice, and whenever own voice comes, use a different program to process that own voice. So that's why it is called own voice processing. And the objective of that is to be able to hear your own voice and so on. Okay, so what we have done till now is we have gone through the different types of hearing problems. We have gone through the features, the add-on features which the human ear has along with the process of hearing. And when a ear gets impaired, how those add-on features are getting affected. And then we also saw the current areas of research or areas of current research focused on improving the technology of hearing aids in the noise reduction part, in improving the own voice processing, involved in finding out the environments which you are passing through and adjust the programs accordingly. So now, with this in mind, with this background in mind, now let me take you through the different processing, three major areas of processing which happens in the hearing. So we should not forget that the primary function of the hearing aid is to process the acoustic stimuli such that the signal reaching the inner ear is as close to the signal that would be presented to the inner ear otherwise. So to achieve this, basically the hearing aid has to do 4 different levels of processing. The first one is called channel separation. The second one is frequency dependent gain. Third one is level dependent gain. And the fourth one is noise reduction. Okay, these are the 4 basic processing schemes involved in hearing aids. In addition to this, there are several other features, but a basic hearing aid should have these 4 processing. Okay. So let us see how this processing is done in. So when we fit a hearing or when we program a hearing aid, the basic objective of the programming is that this curve is called target gain curve. So this is frequency, this is the gain. So this target gain curve says how much gain is required in each of these frequencies. So if you look at this, at 250 Hz, the gain required is 30. At 500 Hz, the gain required is 35. At 1000 Hz, it is 45. So So this target gain curve varies from person to person. It depends on your hearing test, the values which you have plotted, and I have shown you the results of audiometry right ear, left ear, the level at which you are hearing. Okay. Based on that, this target gain curve is formed out. Okay. Now we have to fit this target gain curve into the hearing. That means when a sound of 250 Hz comes, the hearing aid should automatically give a gain of this. When a sound of 500 Hz comes, it should give a gain of this. When a sound of this comes, so that means whenever a sound reaches the hearing aid, first it has to identify the frequencies in that sound. It has to split the sound into those frequency bands. So here you have 1, 2, 3, 4, 5, 6 frequencies. So basically you have to separate the incoming sound into 6 frequency bands. Okay, this we call as channel separation. And this channel separation can be done like this. This is called the filter band approach. For each frequency, you have a filter band. For example, here the band will be say 0 to 250 Hz, 250 to 500 Hz, 500 to 1000 Hz. So you basically slice the signal or separate the signal into these frequency bands. And after separating it, you know how much gain has to be given to each of the frequency bands apply. Okay, so you define the transfer function of the filter so that the sufficient gain is given. So this is the basic approach for giving frequency dependent errors. What you are doing is you are taking a signal, speech signal, and separating it into frequency bands. Okay, so this is like you take a sheet from your book, you cut it into 4 parts, and then rejoin it. However efficient is your rejoining, or however good is your rejoining, the rejoined paper will look differently from the paper before cutting. The same thing happens with the seeds. Okay, so you have to do this. You have to split it into frequency bands to give frequency dependent gain. But when you cut it, give the gain and rejoin it back to lose many of its natural qualities. Okay? So many of the features which your human ear is able to do, you will not be able to do this, because this approach divides the signal into a fixed number of frequency bands with fixed bandwidths, compress the band signal and recombine them to form a single output. Now, to overcome this, the latest technology which the hearing aid uses is something called as a controllable filter. Controllable filter. So in this controllable filter, of course, so this is a newly implemented technology. So what it does is it avoids splitting the signal into different frequency bands. Okay. So you see, if you see here, it has got 2 parts of processing. This is one part which we call the audio part, and this is one part which we call as non-audio part. Okay. So the signal which is picked up by the microphone, it goes to the DSP directly, it goes to the earphone after processing. It doesn't involve any splitting, but we have to implement the frequency dependent gain. For that, what we do is we take a portion of that signal, okay, and use a warped FIR filter here. Why warping is required? We'll come to that later. So this warp, using this warped FIR filter, the signal goes through this warped FIR filter, and what we have to do is we have to feed the coefficients to the filter for each frequency. Okay. So from using this processing stage, you will find out what are the frequencies in this, and what are the intensities, the power estimation estimates, intensities in this one, and then derive the gain which is required, which is as per our target gain curve, design the filter coefficients and do it here. Okay, so this stage does all the separation and things like that, just to arrive at the filter coefficients. Whereas the original signal goes through this filter as a single signal. where the coefficients are varying according to this. So this approach is called channel-free processing. It's not divided into channels. The entire signal is taken, but the individual frequency-based gain concept is taken. So, coming to the question, why we use warping? So this is the spectrum of the human cochlea. In the beginning, I mentioned that it has got three sections. The human ear has got three sections: outer ear, middle ear, and inner ear. In the outer ear, the tympanic membrane is there. So sound reaches as pressure waves, vibrates the tympanic membrane. Then it has got three bones associated with that. These three bones vibrate along with the tympanic membrane. And finally, these vibrations are taken to the inner ear, which you call as top. So in the inner ear, the signal transformation happens from the vibrations to electrical impulses, because the brain can recognize only the electrical impulses, not the vibrations. So when this transformation happens, the cochlea it's like a coiled structure. The length of the cochlea is just 25 millimeter, 2.5 centimeter, and it is a coiled structure. Each portion of the cochlea responds to a specific frequency region. So starting from the base of the cochlea till you go to the end of the cochlea, each region of the cochlea responds to different frequency bands. Okay? So it is said that a normal cochlea of a human ear can respond to 1024 frequencies differently. So that means the cochlea is as good as a 1024 band filter. Okay, 1024 bands filter. So if you have to mimic the cochlea, you have to divide the signal into 1024 bands and then process it. It becomes very difficult. So for convenience, research has identified 17 frequency bands, which are the most prominent frequency bands. Okay, so the 1024 band frequency bands of the cochlea are now reduced to 17 frequency bands. And as you see here, the number of frequency bands in the low frequency region are more, and when it comes to high frequency, the bands are less. Okay, so this is called warping, where you have more number of frequency bands here and higher number of lower number of bands here. So this concept we will be using in finding the coefficients for the filter. So what it does with this technology, what the major advantage is that you are not cutting the signal into pieces and you are taking the signal as such, but achieving the desired gain for frequencies. So now we have seen the channel separation and the techniques used for that. The basic technique, which is based on the filter band concept, and the advanced technique, which is based on the controllable filter technique. So once the division is done, or once the frequencies are identified, you are able to give the frequency dependent gain into that. So channel separation and frequency dependent gain.
3 minutes.
Okay. So the next processing which we have to do is called level dependent. So now, till now we were talking about giving gain based on frequency. Okay. Now we have to take one more issue here. We have to assign gain depending on the level of the signal. Okay. Our human ear has got a very wide dynamic range. We can hear 0 dB also, and we can hear 120 dB, 140 dB. 120 dB, 140 dB is the sound which is produced by a cracker which you use in the wall. Okay? So those small bombs which children burst, if you measure that will be 140 dB. That also the ear can listen, and on murmur also you can listen. So So that is a very wide range. Now when you have hearing problem, what happens is you are unable to listen to the low intensity sounds. Right? The graph which I showed in the beginning says that for that person to hear, the sound should be at least 55 dB. Okay, so you are hearing at this level, but that person is hearing at this level. So your lower limit of hearing has enhanced. Okay. Now, with the hearing loss, one more thing what happens is the upper limit which you can tolerate gets reduced. Okay. So overall, this window gets reduced. Okay. So that process we call as dynamic range compression. So your dynamic range, when you are not having any problem, was this much. 0 dB you can hear, 120 dB you can hear. With the problem, this has come up, this has come down. Okay, so your overall dynamic range is reduced. So that is what is shown here. For this particular person, his dynamic range is this. So whatever we are giving from the hearing aid, we have to make sure that it is in this dynamic range. And now you see this dynamic range, it is not two parallel lines, right? It is this much here, then it is changing here, then it is changing here, then it is changing here. So that means for each frequency group, this dynamic range is different. This is one other complex challenge that we have to face in hearing aid procedure. So that means when I identify the frequency, along with the frequency, I have to identify the level of the signal. If the level is more, I have to give less gain. If the level is less, I have to give more. And that too, that gain is dependent on frequency. So this scheme of processing where the level dependent gain is implemented is called wide dynamic range compression. So the aim of this or the objective of this is to reduce the large range of input levels a hearing aid wearer encounters negative, because you do not have any control over the sounds which you are listening. If it is a loud sound, if somebody is wearing the bursting the clapper, you have to listen to that. There is no other way. Okay? If somebody is using a very low voice, if you have to listen to that, either you have to ask him to speak loudly or you have to use some other method. Okay? So the range of sounds which you are going to hear, that is not in your control. Whatever is the range of those sounds, you have to take that, compress that into the dynamic range of the listener. So when the incoming sound is divided into multiple frequency channels, we have to have different compression characteristics. We are not using the word gain here because in some cases we have to give gain. When the sound is too loud, we have to compress it also. That's why it's called compression characteristics. Okay, so we have to implement that. Then it becomes multi-channel wide dynamic range compression. So let us see how it is done. I'll just take the example of dividing the signal into two frequency bands and how it is done. So when the incoming sound comes, first we divide it into two frequency bands. Then you have to do the level measurement. Okay? So in this frequency, what is the level, and in this frequency, what is the level. Okay? So you know that basically we use two types of sounds for our communication. One is called vowels, the other one is consonants. Okay? So R, E, O, U, they're all vowels. They are low frequency sounds. The maximum frequency of a vowel can go up to 800 Hz. But the consonants like ka, pa, cha, sa, sha, they are all high frequency sounds. Sha is the highest frequency sound. The frequency of sha is from about 2500 Hz to 7500 Hz. Shh, that sound is high frequency sound. So that's why we have to do this division. Okay? Now it is very easy to hear the vowels because the vowels has got very high energy. But it's very difficult to hear the consonants. Like sh, s, the energy level is very less. So you have to divide it into frequency, find out the level. So what I'm saying is that when you divide it into two frequency bands, low frequency and high frequency, The vowels are low frequencies whose level is quite little. Okay, the consonants are of high frequencies, the level is very less. So in the same word, say for example the word kashtam, kashtam, okay, ka is there, then I is there, ish is there, the consonant is there. So each of them are at different levels. So that's why we have to separate them into frequencies and identify the levels of it. If we don't do that, if we are giving the same gain to all, what will happen is the high intensity sounds will become more louder. The low intensity sounds, which have to be more louder, will not become that much louder. Okay, so just imagine in that word kashta, if you miss ish, total meaning is different. Right? Total meaning becomes different. So when you process with the hearing aid, you have to look into that area. We'll stop here for a break and then we'll come back. Hope you are following me. If you have anything in between, you can pause me and ask me. Signal and difference of frequency difference are. Now we started with dividing the signal into two frequencies. This I have just taken as an example. Don't think that it is only for two frequencies. It depends on the hearing loss pattern of the individual. As many number of frequency division you have to consider as the variation in hearing loss of the okay, so as an example, just to show the process, taken two frequency divisions here. Then the level measurement is done individually. Okay. Now we have to implement the level measurement. So based on the level, we have to assign the gain. And that is done with the help of a compression characteristic. So if you see here, you have two compression characteristics here. This compression characteristics is the one which goes and fit in here. This compression characteristics which goes and fit in here. Now if you see this compression characteristics, it's just it will just tell you how much gain has to be assigned depending on the level of the signal. So for example, this is the input level. When the input level is 40 dB, the gain given is only 10 dB. In this, whereas the same input level of 40 dB will get a gain of 40 dB. Okay, so for this group, you are giving this much of gain. For this group, you are giving this much of gain. So like that, when the number of divisions increase, for each division you have a different combination characteristics. So it's just like a lookup table. See the input level because you have already measured the level. Based on the input level, you assign the gain. Okay. Differently for each frequency group. So once that is done, again you based on the compression characteristics, assign that gain to each of the channels and then so this is how the level dependent gain is implemented. So now this level measurement system, again our ultimate goal is to complete all the processing within 8 milliseconds. The processing time should not go beyond 8 milliseconds. So that means this entire process you have to complete within 8 milliseconds. Now the issue here is the level measurement process is a time consuming process. Now when you measure the level, I can measure it every 1 millisecond. I can measure it in 10 milliseconds. When I measure it in 10 milliseconds, I have to take the average for that. If my measurement time is 30 milliseconds, I have to take the average for that. If I take a very short time, there will be wide variation in that level. It will be, the gain will be changing very frequently. It will be very irritating to the user. If I keep it too big, if the measurement time, if I keep it too big, then it will affect the processing time. Okay. So that is why this level measurement function or level measurement algorithms are very complex. And if I have to divide the signal into say 12 channels, I have 12 level measurement systems, which will increase the complexity of the processor. The processor has to be a higher end processor. The data load of the processor will increase. And if that processor becomes more and more complex, it will be very difficult to fit the processor to actually the hearing aid has to be completely hidden, and it is not behind the ear or in the ear. You have size limitations, so you cannot increase the size of the processor. That is one thing. Second thing is it is a battery operated device. Okay, just like you have watch cells for your watches, those kinds of cells are used in hearing aids. On an average, the cell lasts only for 3 to 4 days. So if the processing load on my processor increases, it consumes more power, and you cannot use even one battery for 1 day. So you have to consider all this when you design this. So that's why effort is made to reduce the amount of processing as much as possible. Now, if you have say 12 frequency group, and if you need 12 level measurement system individually for each group, it becomes a load onto the processor. So nowadays, a solution is being done in this way, where you have more number of frequency groups, but the level measurement is common. Now, if you see the centers, this is divided into 2 frequency channels. You have individual level measurement system for each channel. Whereas here, it is divided into 2 frequency channels, but the level measurement is common. That means this level measurement system will measure the level for the main signal, but the compression characteristics are different. Okay, so if dividing it into low frequency and high frequency group. For low frequency, the gain which you are going to give is different, even though the level is same. The gain which you are going to give is different. For high frequency, the gain which you are going to be given is different. Okay? So therefore, you are reducing the number of level measurement systems. This is to optimize the processor, to reduce complexity or to reduce the calculation load on the processor. This is being done. So this is one of the latest developments with us. So now, after doing the frequency dependent gain and level dependent gain, the next issue which we have to tackle is the noise reduction issue, which is the most complicated or most complex issue as far as hearing aid signal processing is concerned. So now I have been telling about the surveys, and one survey which was done a few years back found that a person of that age, maybe 70 plus, when he has hearing problem, probably he goes to a center, get a hearing aid for him. He will use it for 1 or 2 months. After that, he will know that he will be so this has become a general feature. So a study has done what prompted them or what made them to use their hearing aids in drawings. Okay. So the respondents, the study was done on almost about 10,000 people, and the respondents, they said that the first reason they said is the device is physically uncomfortable. So you have different types of hearing aids. One type is worn behind the ear, just like the always text. It is worn behind the ear. It will not be visible. It will lie between the earlobe and the auditory part here. Those hearing aids are called behind the ear because it is worn behind the ear. Another type can go into the ear, which is called in the ear. Okay. Another type can go completely into the ear canal, which is called in the canal. Whatever is the type of hearing aid, when you put it here, it is irritating to the user. So it becomes physically, the device becomes physically uncomfortable. The second issue which they say is that it does not perform well as expected. And the first factor in that is too much background noise. Background noise is too much. Now, you are listening to me. If I make some sounds here like this, you are not hearing that sound because you are listening to me. But when you use a hearing aid with such high gain, even you will be able to listen if this page is done like this. That sound becomes so irritating to you because this is a soft sound. The hearing aid program, we have trained it to enhance the soft sounds with more gain. Which soft sound it should enhance and which soft sound it should not enhance, we are not taking it. So these kinds of, if this fan rotates, it becomes like a noise for them. Okay. So too much of background noise. Then too much feedback. Now, you know that when we use systems, mics like this, you must have heard in calls and all, it starts howling, it starts making a howling noise. The immediate thing what we will do to prevent that howling is either reduce the gain or move away from the speaker, loudspeaker. Okay? Here, the microphone and the speaker are very close by. In a hearing aid, the microphone and speaker are very close by. So the chances of this feedback are very high. The moment it gets a feedback, it produces a whistling sound. You just imagine the whistling sound straight coming to your ear becomes very difficult for the person to do. And third is this word sound. We feel that the sound which is coming through the hearing aid is totally different in quality than the sound you listen. So this part, this background noise part, is still a major limitation in hearing aid. And I did mention at the beginning that the most complex thing in hearing aid is to tackle this noise because the sound which you want to listen and sound which you don't want to listen are in the same spectrum, same thing. Okay, so the lowest satisfaction level of 50% was observed when the hearing aid where users were trying to listen to a conversation in the presence of others. Okay, so when you are trying to listen to a person, when a function is going on, when you are trying to listen to a person in a railway station, when you are trying to listen to a person in a bus stand, it becomes very, very difficult. Now, one more issue which adds to this is we have about 50 lakhs hearing aid users in India. As well, it is 50 lakhs of people are using hearing aid. All these hearing aids, not even a single hearing aid is manufactured in India. All these hearing aids come from outside. And the programs, the algorithms in these hearing aids are from outside. Now, those who have gone to other countries know that take the Mysore bus stand and take the bus stand in San Francisco or Los Angeles. Okay. The bus stand in San Francisco is like this classroom where you cannot hear any noise because the buses will not produce horn. Okay, people will not talk. So the program which is designed for the bus stand in San Francisco, the same program you are using in Mysore when you go to Mysore bus stand. Will it be okay? Okay. So this is exactly what is happening here. So that is why now we have thought of having programs for our own situation. Okay. So now they also have found because their market is good in India, they also has found out this problem. So what they have done is instead of designing it for our bus stands, they create more noise there, artificially more noise there, and they send algorithms there. That will not be suitable for our case. Okay, so that is the reason the lower satisfaction level is 50% when people are trying to speak in the presence of noise. So I put this slide basically to give you the importance of this noise reduction algorithm. And I've also mentioned in the beginning that it is not noise elimination. We are trying to reduce the noise so that the difference between the level of the speech and the level of noise are in the perceivable limits. For a normal person, the difference has to be 5 dB. But a person who is using the hearing aid with already an impaired ear, it it has to be 50. So all the noise reduction algorithms concentrate on bringing this level, bringing the speech to noise ratio to plus 50. So this cannot be done by using one technique. It has to be done by using parallel. So there are two popular techniques which are used for noise reduction here. One is noise reduction through signal processing. Second is noise reduction using microphone. So we'll see the basic concept, how noise reduction is implemented through signal processing, how noise reduction is implemented using microphones. Now, this is a signal which is totally masked by noise. So what you see here is the word understanding. The word which has been recorded here is the word understanding. So if you see this portion when no word is spoken, and you see this portion when a word is spoken, you don't see any difference. It's full of noise. Completely, we'll say that it is completely masked by the noise. Okay. So we have to reduce the noise in such a situation. How will you do? The speech is also the same, the noise is also the same. Okay. So one technique which we can use in signal processing is the first step is you split the signal into different frequency bands. Okay, so this is my signal. This has been recorded for the word understand. What I am going to do is I am going to split the signal into three frequency bands. The first one is 0 to 500 hertz. The second one is 500 hertz to 2 kilohertz. The third one is 2 kilohertz to 4 kilohertz. When I divide it into three frequency bands, this is what I got. Okay? So in this frequency band, this is a signal I got. In this frequency band, this is a signal I got. And in this. Okay? So by looking at this, we can say that the noise is masking the speech signal in this band more compared to this. So here you are at least able to see the speech. Here also you are at least able to see the speech. Okay, so now I found that the noise is more prominent, it is there everywhere, but it is more prominent in this frequency band. Okay, so what I have found is the noise is masking the speech signal from 0 to 500 hertz. It is significantly less here, 500 hertz to 2 kilohertz, and it is minimal. Okay. Now, how will I be able to use this information? My ultimate aim is to reduce the noise. So, what should I do now to reduce the noise? What can you do now to reduce the noise? So, you have to give more attenuation to this frequency. If you give more attenuation to this, the noise will get. But the problem is you have speech in that also. Okay? So when you give more attenuation, the speech will also get affected. But the effect of noise will be less. Okay? So what I have to do is, now when I am taking this and seeing in an oscilloscope or any speech analysis tool, I can manually find that this is the noisiest channel. But the hearing aid should automatically find it, right? Now by looking at the signal, it's very clear to me that this is the noisiest channel. The same thing the hearing aid has to do on its own. Okay? It has to find out which is the noisiest channel. To find out the noisiest channel, what is being done is the envelope is taken. Like this one, it just takes the envelope. Okay? It is taking the envelope of this. It is taking the envelope. So I have taken the envelope of all the envelopes. And then you can see a green line and a red line here. The green line is just following the maximum. And the red line is following the minimum. Now if you look at the, you find that the difference between, we call it as running maxima, the difference between running maxima and running minima are less in this channel. Right? Whereas the difference is maximum in this channel. So that means to find out a noisiest channel, I have to see this difference. Wherever the difference is less, that is the noisiest channel. Okay? And wherever the difference is maximum, that is a channel without much noise. So now, after finding out this, I have to follow the running maxima and minima, and then I have to provide an attenuation which is inversely proportional to the difference between running maxima. So wherever the difference is less, I have to give more attenuation. Less difference, more noise, more attenuation. More difference, less noise, less attenuation. So based on the difference between this running maxima and minima, we'll decide the attenuation which is given to each channel, which is inversely proportional to the difference. After that, after I do that, this becomes my signal. So I have given more attenuation to this, the noise has reduced. Medium attenuation to this, and less attenuation to this. Okay? So provide attenuation which is inversely proportional to the difference between maxima and minima. After doing this, then I'll finally recombine all this. So when I recombine, the output signal which I got is this. Is this different from the previous one? Is this different from the previous one? My input was this. So now you see the difference. At least you can make out that some speech is here. So the speech to noise ratio, it was very bad here. It was in minus here. Has improved to plus 10. Just by doing this. So this is one technique where the signal processing is used to enhance the speech to noise ratio. But the limitation of this technique is that by eliminating this channel, 0 to 500 Hz, there are many speech sounds in that. Many of the vowels, so for example, the vowel O lies in that. Okay? So that level also will get reduced along with that. But something is better than nothing. Here it was nothing, no speech was audible. Here, at least you are able to hear the word because the speech to noise ratio has increased. The next type of, or the next technique which is used for noise control is using the microphone itself. So, the microphone which is used in a hearing aid is a very small one. It will be the size of a, what do you call it, a wheat seed. That is the size of the microphone which is used in. And it is a very costly component. 25% of the cost of the hearing aid is the cost of the microphone, because to make the microphone in that miniature size, it's very expensive. I have gone to this manufacturing facility of this microphone in Denmark. So there, what I have noticed is that when they make 100 microphones, only 1 or 2 of them pass the quality test. Remaining 98 will go as waste. So that's why the cost of this microphone is very high. So this microphone, since it is very costly, we have to be very, very careful in using that. So one way of using these microphones for noise control is by using a 2-port microphone. 2-port microphone means sound can enter into the microphone through 2 ports. This is one port, this is another port. And you know that the microphone works by converting the pressure changes into electrical signal. So basically the microphone has got a diaphragm, a membrane. You speak into the microphone, the membrane moves. The movement of the diaphragm is converted to an electrical signal. So here you have the diaphragm. This diaphragm, this front port, this we will call as the front port. The front port opens into this cavity of the diaphragm, which we call as frontpodium. The back port opens into this cavity, which is called as the back. So this is the microphone. It's an expanded view of that. This small tube type thing, what you see, is the front port. So sound can enter into that through the front port, and this is the rear port. Okay. So when sound enters into this microphone through these 2 ports, the movement of the diaphragm will be based on the difference in pressure between these two. Okay. So if the same sound is entering through both the ports, the membrane will not move at all. The pressure of the sound entering from this side, pressure of the sound entering this side, if they are equal, it will come. Usually, when we talk to a person in a noisy condition, we'll be like this. If I'm talking to madam, she's in my front. Okay, so that means that time the sound which I want to listen comes from the front direction. So this port, the front port, in the hearing aid, it is oriented towards the front side. Okay, so when I'm talking to you, the sound which is coming through the front port is the sound which I want to listen. But along with the sound, noise also will enter, because noise is there everywhere in that environment. So what I'm getting in the front port is the sound which I want to listen plus the noise. Now what about the rear port? The back port, what I'm getting is only the noise. Right? This is in the front, this will not go to the back side. Okay? So what I'm getting here is the signal plus noise, and what I'm getting here is the noise. And what this diaphragm will do is do A minus signal plus noise minus noise. So noise gets cancelled. So this is one way of doing that. Now, for this to happen, we have to be very, very sure that the sound which I am listening should not enter into the rear port. That's why you have a damper here. This damper this is an acoustic damper made of some material. This damper will prevent the entry of the front sound, but it will allow the noise to go because the noise is of much higher intensity. This sound will be stronger here but weaker here. So the weaker sound will be attenuated by the damper. So using this, you can do the noise control. So the technique is like this. You have the front port going to the diaphragm, sound coming from the rear port, passing through this acoustic filter, going to this. The difference between the two are converted into electrical sound. So this is one basic way of doing integration here. So in a hearing aid, it will be like this. The microphone will be placed here, the front port in this direction, rear port in this direction. The second way of doing this is by using two microphones. Okay, this is an actual hearing aid. You can see that it has got two microphones. Microphone 1, microphone 2. In the previous case, the problem is it will be very effective if the sound is exactly in the front. Okay, suppose I'm talking to him. At that time, if somebody calls me from back, or if somebody talks from the back, I will not be able to listen to that, even though that is important for me. Okay, so that's a serious limitation in this case. That limitation we are going to avoid with this. But here the cost will increase. There it was only one microphone. Here you have two microphones. The cost will increase. If it is a hearing aid of 15,000 cost, the increase will be 3,000, 4,000. There's an additional problem. But this is much more effective. How it is more effective? Let's see. So here you have two mics. There you are having one mic with two ports. Here we are going to have two ports. One is the front mic, the other one is the rear mic. Both the mics convert the sound pressure into electrical sound. Now there you are using an acoustic filter whose characteristics is fixed, permanent. You cannot change that. Here you are going to have an electrical filter whose characteristics can be changed. Okay? So now when you get the signals from these microphones, you decide which one you want to make as front mic, which one you make as rear mic. So it will identify if the sound source is from the back, that will be made as the front mic. If the sound source is from the front, this mic will be made as the front mic. So it is adaptable directionality. In the previous case, it was fixed directionality. Here, the sound can be from any side, the noise can be from any side, by detecting from the signal, it will decide what has to be done. So this filter characteristics are programmable. So this kind of noise control is called dual microphone system. So the directional pattern of the microphone can be changed. This can be made front mic, this can be made rear mic, just by adjusting the filter characteristics. So depending on the situation, you can adjust the characteristics of the next technique, the recent technique of doing noise control is by changing the artificial model for. So here the concept is they have taken the data of 12 million types of sounds. So any sound in the world you take, it would be one of these 12 million sounds. Okay. Any noise in the world you take, it will be one of these 12 million sounds. So your microphone is here now. It is watching the noise here. It will take that signal and then it will do the comparison with all these 12 million. Okay. It will find a match. Okay. Now when I find a match, I know that this is that particular noise. This is a noise from a party hall, or this is a noise from a bus stand, or this is not the noise from a station. Okay. For that, I require the data of this. This data is there available with them with their situation. This data is totally missing in our situation. Okay. There is no data available for what is the kind of noise in our bus stands. And bus stands also it differs. The village bus stand, the city bus stand, the town bus stand, the noise levels will differ. There is no data. If this data was available with us, we could have easily implemented. Okay. So now we have hearing aids with artificial intelligence, which work on this principle. They already have the data of 12 million types of sound sources. The moment the microphone is in a situation, it will take that data, compare it with, well, using a tree approach, cluster approach here, and then identify the source, and immediately implement what is required for reducing the noise and situation. Last, we'll move to the processing of onwards. So I've told you at the beginning that this is another complex task which the hearing technologists was onwards concerns around the most common post-fitting problem. Post-fitting means after you start hearing, there is a problem will start. So what is being done for that is it automatically changes the gain when the person is talking. If I am using a hearing aid, okay, in a conversation, sometimes I will be talking, sometimes the person to whom I am talking, he will be. So when I am talking, the processing characteristics will be totally different because I don't need much gain, because I know what I am talking. I have to hear that just to make sure that whatever I am speaking is audible to the other person. But I know what I am speaking. So I don't require that much gain or that much processing for my own voice. But the hearing aid should automatically identify my speech. So on voice processing automatically changes the gain and output when the hearing aid user is talking. So when I am talking, the gain and output is automatic. And then instantaneously readjusts to program it immediately for the reference. So once I talk, say if I ask what is your name, after that the other person has to respond. And the other person responds, the characteristics will be totally different. Okay, so this will make my own voice perfect. Okay, so you may be thinking now that why so much of importance is given to this. I'll tell you, 50% of the people above 60 years of age who come to our institute for making their hearings, they complain about this, that I'm hearing my own voice differently. So much of, they say that something is ringing in the ears when I talk. a high-end hearing which costs 30,000 above. So what we do in the other hearings which are low cost hearings is we reduce the low frequency gain little bit so that all noise is not. That's the only thing which we can do. Whereas hearing aids with these features, it has got facility to have so whenever patient is speaking, the bilateral data sharing, processing and analysis, the hearing aids identify the signal that they indicated signal for on voice process. And now towards the end of my talk, the gaps in the signal processing. So one major gap is, as I told you in the beginning, we are doing all these processing with the natural signal. And we are deliberately altering the characteristics of that. We are increasing the gain in some area, we are reducing the gain in some area. So when this is done, when we do this, when we do the deliberate alteration of the incoming speech sounds, it inadvertently alter the temporal characteristics. Now when a speech signal is concerned, there are two types of characteristics. One is the temporal characteristics, which is concerned with the time and duration. Second is the spectral characteristics, which is concerned with the spectral content of the signal. Both are equally important. Ultimately, what we get from hearing a speech is that we should be able to comprehend that and converse with others. We should be able to understand what he is saying. And to understand this, both these characteristics have to be intact. So I gave you the example of the word kashta, which has got the vowels, low frequency, and the highest frequency consonant ish. Now to hear the word as kashta, there is a proper proportion of the level of the consonant and the level of the vowel. If the vowel is of this level, if the consonant is of this level, you can hear both vowel and the consonant, which is called spectral contrast, which is a very important property in this case. If the spectral contrast is spoiled, as we are doing in our case, because we are doing different gains based on the frequency law, the spectral contrast will get spoiled. When the spectral contrast gets spoiled, it will spoil the naturality of the signal. Okay, it will sound totally different to the user. Okay, so we have to have a compromise. The naturality should not be spoiled, whereas the processing is required because to compensate for his hearing loss, the consonants which are of low intensity has to be enhanced. So that is one gap in signal processing. There is no effort to maintain naturalness in the speech. All the processing is based on his hearing pattern. Whatever way things have to be altered, we are altering and putting it into his ears so that he can hear this sound, he can hear this sound without much problem. Thereby altering the okay. So efforts have now started to work on this. You can see this paper is on 2019. So he has found that this is the problem which the hearing user faces. The second is, as I've already mentioned, about the spectral contrast. So this is about the temporal contrast, this is about the spectral contrast. I'll give a little more detail about the temporal contrast. What does it mean? Sounds like pa. Pa is a sound. Ka is a sound. So they are called as stop consonants. Consonants are divided into different categories. In that, pa, ka, ba, they are all known as stop consonants. Why they are called stop consonants is that in that production, if you notice, to produce pa, the first thing what you do is close all lips like this. Pa. So from there it starts. Okay. So we are stopping the airflow there. There is no airflow there. That's why it's called stop components. Okay? So first thing is that stop. So when we stop the airflow there, and suddenly we open, there is a burst of air coming out. Okay? So that event in the production of what is called burst. This burst, if you see the speed signal, you can clearly see the burst. So if this burst is very important in producing this power. If that burst is not properly produced, power will become bar or it will become fog. Okay? So this is a temporal event. The timing of the burst is very important. The time duration of the burst is important. The amplitude of the burst is important. After that, the remaining part of pi is nothing but your R sound. So first is this closure, then burst of air, then after a certain gap, your R comes. So this closure plus burst of air plus your R sound makes the sound pi. Now there is a gap between this burst and the voice, the R sound. That gap is called voice onset time, the time taken for the voice to start onset. That is also very important. So like that, any sound you take, it has got very minute temporal features which are related with the time and its amplitude. If that is lost, you will not hear that sound. So you must have noticed some poor microphone systems which are used for this public address and all in religious places and all. They're very low end systems. So many sounds when you hear through that system, it will be heard as a different sound. Pa will sound as fa, pa will sound as something else. Yeah. It's all because you are spoiling the temporal patterns. Imagine a hearing aid user hearing all those sounds like this. How irritating it will be. Half of the sounds or half of the words he will not be able to understand. Okay. So the retaining temporal and spectral features is very important. But the first priority we should give is to make the sounds audible. To make the sounds audible, we do all these exercises and finally spoil the temporal and spectral characteristics. So this is a big gap in signal processing technology. Okay. So now several attempts have been made to close this gap. Okay. One such attempt which is being done very recently is when you talk to a person, you look at his face and talk. Even though half of the things you will not hear properly, just by looking at his lip movement, you will be able to clearly identify what he is speaking. But when you are using the hearing aid is totally not aware of this. It is only listening to the sound, processing the sound. So now what is being done is a small camera is fitted along with the place where the microphone is fitted, there is a small camera. This camera tracks the lip movements and synchronize your process the sound along with it so that these temporary events are not. Okay, so this is in the research stage, it's not implemented in any hearing till now. So there, the perfect integration of image and speech processing will come. You have to synchronize. So when I say wow, so the moment the lip closes, your processed speech sound has to get synchronized with that. Okay? And when the moment you produce up in pa, that point has to be synchronized with that. So that is one research which is happening here. And basically that is done to close this gap between spoiling of temporal and spectral characteristics of the speech signal when you are processing this. Okay. So with this, I come to the end of my lecture. If you have any doubts.
Application of whole voice processing. Can you just give me a real-time example? Why is this actually required?
So why it is actually required as when you are speaking, okay, if you are wearing the hearing aid, when you are speaking, you are hearing your own speech through the hearing aid, right? Whatever you are hearing will be through the hearing aid because your ears are completely blocked with the hearing aid. So imagine your own speech you are hearing with the hearing aid. Okay? The hearing aid, if it doesn't do anything special for own voice processing, will process your speech as if it processes the other speech. Okay? So that means that sound becomes too loud. So just imagine when you are speaking, you are getting too loud sound, and when the other person is speaking, you are getting a very loud sound. So this too loud sound becomes too much irritable to you. So what you do naturally, you will reduce your voice by speaking. But at that time, the other person will not be able to hear that. Okay? So when it becomes too much of sound in my ears, I'll reduce my level. When I reduce my level, the other person will not be able to hear that. So I will speak, I'll ask what is your name. If you are not responding, I'll become a little angry. Right? When I am not getting any response. So this is a problem with on-voice processing. So what?
Something like that when you're calling, your voice will be repeat.
Exactly. Sometimes in the mobile you
Mobile
get
when you're calling.
so irritating, right? Same thing happens if you do not have exactly. So you sense your, and when you are speaking, you sense that at that time reduce the gain. And when the other person is speaking. So two different programs in the game. One for your own. Very good question.
Sir, you said that the hearing aids are all imported or not. What would be the reasons for it?
Another very good question. Efforts have been made to develop the hearing aids in India. In fact, we were also part of that. It was a big project by the Ministry of Information Technology, and the lead role was taken by the CELAC Toronto. We developed everything. We made the chip for that. Fabrication of chip is very, very difficult because if you have to make 10 chips or 1,000 chips also, the cost is almost the same. So in spite of all that, we have made the hearing aid is. Now, after making the chip, we found that the current consumption of the chip is too high. But we have already made 1,000 chips. Okay? So when the current consumption is high, nobody will use that. You have to change the battery 2 times in it. Now about the import, there are only 5-6 manufacturers in the entire world manufacturing these technologies. Okay? They are like suppliers all over the world. For them, this number is not an issue. Okay? So they'll keep on developing their technology, change their technology. It's just like mobile. Every 6 months the technology changes because there is competition. If you have to sell your hearing aid, you have to have an extra feature. And many of the features which I've discussed are from different companies. Each company has a different feature. Okay? Now you have to invest in all that. Where will the money come? When your volume of business is high. Okay? The chip cost will come down when your volume is high. So that is the reason it's not. So this hearing aid developed by CELAC, it is available online. You can go to CELAC site and still order for that hearing aid. It's called Shruti. The name of the hearing aid is Shruti. You can online, order it online. It costs just 6,000 rupees. It has got all the features in this hearing aid. But the problem is, and when the current consumption is more, one more thing which will happen is the noise becomes high. The electrical noise which will be converted to sound noise, that will also be high. So the noise in that hearing is also high. So it is the volume which matters.
Sir, you told database is 12,000. Will it include all the signals in that 12,000 or any difference in the signal is there?
It's not 12,000, it's 12 million.
12 million.
12 million.
Is it included in 12 million? Or
12 million includes all the sounds possible in this world, including the musical
Is
sound.
it exact or is it nearby?
It is exact. It is exact. It is from naturally recorded sounds. So they have recorded 12 million sounds in different situations, but I repeat, it is based on their system, not for the Indian system. Right? So their worship place, totally silent with all good acoustics, AC and all, will be totally different from our worship places. Like Chamundi, where it is totally different. So those 12 million acoustic samples which they have considered do not include our installations.
If we include Indian version means, will it increase or decrease?
If we include our this one, it will enhance the performance in our situation. Okay, so now most of us are not happy with the hearing aid just because of this, because it's not truly responding to us. Otherwise,
So number of channels for proper hearing.
that depends on your hearing level. So when you go for audiometry test, you are tested at different frequencies. If your hearing loss is almost same for all the frequencies, the number of channels will be very less. But if it is varying like this, for this channel it is something that's for this frequency, then you require more.
To make hearing
So
loss.
normally 4 channels is enough. For a normal hearing loss, we call it as flat hearing loss, which is almost same in all the frequency. 4 channels. Okay. But if it is too much of variation, even you can go up to 16 channels.
Sir, what about putting the artificial models, the AI devices, reset,
Huh.
devices? What about the concepts of power consumption, cost?
No, that depends on the DSP chip. Okay. So that has nothing to do with the artificial intelligence. Artificial intelligence is just a matching problem. You have a set of data here.
For every
Huh.
speed, it has to go, model has to go.
Model has, it is just matching. Matching doesn't consume much of it because there is no calculation involved there. Okay, so you have this, you have to match with. It's a cluster problem. So it goes in clusters. First you find this tree, then the next branch, then the next one, finally. It doesn't take much of the process. It's in fact it saves rather than you. The other way of doing it is you process your signal and find out which it is, which category it is. So the processing complexities are less in matching compared to the digital process, and it becomes fast also. Matching happens very fast.
Why not we use rechargeable batteries?
Rechargeable batteries are now being used. Most of the Indian companies are come with rechargeable batteries. So usually you don't use this in the night time. Night time you keep it for charging. Morning you take it. It works for almost 24 hours. It comes with the 3-year warranty. 3-year. That's being used now.
What is your suggestion, sir? We can select one challenge and go deep into that, or can concentrate on multiple issues of the hearing aid?
Problem by problem. See, first, to understand this, my experience is almost 23 years in this field. Even now, some of the things are not clear to me. But to understand this itself, it will take time. Unless you understand the problem correctly, you cannot find a solution to that. That will not become a perfect solution. That will be somewhat fit into solution and something like that.
Nowadays, every project or any PhD, they are asking hardware kind of research. If you select this hearing aid as our topic, then how we can
You can implement the hardware using an FPD because there you don't have to worry about the power consumption. That's how it is done. Even when we did the Indian hearing aid project, first we did was implementing it in FPD. That was little bigger. Tested it and then converted it into ASIC. So in that conversion to ASIC, the only failure which has happened is the power consumption. Because that you know only after fabricating the ASIC. Before that you know how much it will be.
is there any just like general purpose processor? Is there any
You can implement it in any DSP kit. Data processing. But to prove a research, you don't have to worry about the size and the those are all optimization techniques which happens later. So to prove your algorithm or how efficient is that, you can implement it in replacement. That's how it is being
Any
done.
publicly available data sets and this is like any
Ah, yes, yes. There's noise data sets are there. Many are there. MIT has a data set. And some Australian university also has a data set.
Is there any scope for NLP techniques?
NLP as such, no one has attempted that. Because NLP requires so much of computation. So the limitation in the size of the processor and the power that becomes there. That's right. That much advantage is also not there.
Like to explore more, do we have any facility from the institutes like regarding Enhancement to explore more?
Explore more means the
Like from your organization?
so our strength is basically the number of hearing aids we fit in a year is 20 to 25,000. 20 to 25,000 people take hearing aids from us. So we have got a good clientele set. So advantage is we will come to know their problems. And one more thing, because you have elders at home. One very important thing while doing this hearing aid thing is that the programming part. Because it has got all features. How efficiently you program, the efficiency of the delivery lies in that. So usually what we do is, just like purchasing the medicine, you'll see some board hearing aids available. We'll go there, purchase it in. Their interest is in selling the machine. Because when you sell one hearing aid, 30% straight away commission is there. Okay? What we are giving, being a government institute, the company is giving us at 50% of the price, because that is the actual price. The remaining 50% is their commission to the agents. So we are getting at 50% and we are selling the same hearing aid with the same 50% discount to the customer. So whatever you get in market for 10,000, you will get it for 5,000 rupees from us. So when you go to small vendors or clinics like that, their interest is in selling more number of units. Okay? They will not be able to spend more time on it. When you come to our institute, we take almost 1.5 hours to program one hearing aid, which they will not do, because if they spend 1.5 hours, their number will reduce and their profit will reduce. We don't have to worry about profit, we have to worry about the quality and service. So that programming is very important, and where the experience also comes into picture. Okay? Because he must have, when you wear it, you will tell some problems. He must have faced that problem already, so he knows what is to be adjusted to solve that problem. Each problem, individual wise, it is different. So one example I'll tell you. One of my known person in Mysore, who is our family friend, she is 70-year-old. She came for fitting a hearing aid. So we tried this hearing aid. One hearing aid was okay for her, but she had this own voice problem. So usually, in our case, we have postgraduate students, MSc audiology students. They do the programming. So one student did, second student did, third student did. I was not satisfied. Then I called the senior most experienced person. Within 2 minutes, he solved it. There was one adjustment which had to be done. He adjusted that and she was very happy. Even after she procured this 3 months back, even till this time. So it is very important, even if you spend the maximum and get the most costliest hearing, this programming or tuning, we call it as tuning. Tuning the hearing into your environment is very, very important. If it is not properly tuned, your father, your mother are not going to use the hearing aid at all. They will say that whatever you want to tell me, you speak a little loudly, that's enough. Okay? They'll keep the hearing aid. So it's very, very important. Get the service from a good place where proper experience. There are good private practitioners also. Even in Mysore, there are private practitioners who are experienced. They will spend more time on that because they will not be much invested in money. They will be customer satisfied. So that is very, very important. It's not procuring it. It's like mobile. If you don't know the field, if you don't know how to operate many of the features, there is no point in procuring an iPhone that's suddenly for the programming is very important. Ethical is very important. So usually when we program it, we tell them you walk around, go to the restaurant outside, have a cup of tea and come back and tell us the difficulties which you are facing. So based on the difficulties, we will reprogram that. And then only people will use it. So many, I have heard from many people, for their parents, they purchase very good hearing aids and they use it for 2-3 days after that. So this is very important. As recently, last month, they have fitted a hearing aid for a 99-year-old. She's using it very comfortable. Before coming to take the hearing aid, she had all this apprehension because many of her relatives told that it is a waste, they are not going to use it. But it took almost 2 hours to program the hearing aid for her, and even now she is using it very comfortable. Just now when I was sitting and having tea, so she called. It's very, very important to do properly. You have so many features that can be programmed, so you have to understand the requirements of the client and what you need. So when you procure hearing aids for your relatives or for your elders, keep this in mind. Just procuring a hearing aid that will not solve any of the issues. Properly program it. Go to a good place, where experienced person is there, program it. And it can be reprogrammed any number of times.
Sir, I think the use of AI, ML in hearing aids is limited. Sir,
Yeah, it has
compared to
started.
other
It has-
medical.
Yes, it has started this morning. It has started 2 years. The whole research has started 2 years. It's a good problem.
Yes. The thing is availability of data set, which will work for all the general problems.
What advice you will be giving for students, like who will be putting like earbuds all day? Like right now we are seeing.
It is like the duration is very important. Okay, it's not that you should not listen to loud noise. You can listen to loud noise. You can listen to orchestra, but the total duration is very important. So when you are listening to loud sounds, the mechanism of the ear that will respond to all the loud sounds, but that is under strain. So if you listen it for 30 minutes or 45 minutes, it's not going to harm anything. But if you listen to that for 8 hours a day, definitely it is not. It is the duration which matters. It's not loudness. Suppose you use earbuds, you can use it 30 minutes, 1 hour, remove it, give some gap, again use it. Absolutely no. But you continuously use it, that is called noise-induced hearing loss. You are forcing your ear with more and more of sound. And so in the final stage, in the inner ear, where this conversion from vibration to electrical impulses happens, you have small hair cells like this, the hairs which you have on your fingers. Small hair cells are there. So these hair cells rub against a membrane to convert this impulse. So what happens with loud noise is that these hairs will get spoiled. And once it gets damaged, it's a permanent damage. No more hair cells will come there. So that happens with more duration of time. The ear has all mechanism for self-protection. You must have noticed that when you listen to a loud sound, your ear becomes dumb for some time, right? That is a beautiful process where you have the tympanic membrane like this. You have the first bone in the middle ear like this. So when loud sound comes, what happens is this bone gets detached from the tympanic membrane, so that there is no connection between the outer ear and middle ear. So the total sound is cut off. And after some time it comes back again. So this process is called stapedius reflex mechanism. That is there inbuilt in. But continuously if you keep on listening to crackers, this how many times it can after some time it becomes. So here has all mechanisms to here is a wonderful processor. Go on to learn about it. Your MP3 coding is based on the function of the cochlea. How the cochlea codes and compresses the signal. That was studied and that was implemented as MP3 code. So it's like a big book. Many of the processing strategies which we use in signal processing is taken from the cochlea signal processing.
So which company hearing aid devices better? Can you just mention?
There are 5-6 manufacturers. All of them are, because all of them take the chip from the same manufacturer. All of them take the microphone from the same manufacturer. So like Widex is a company called Widex, a company called Dynavox, a company called Oticon, a company called Resound. All of them are.
Basically, the price differs because of the features.
Price differences because of the
Most
features and level of processing.
For an middle class person who is about, because I had an experience when I inquired, it was from few thousands to lakhs also. So there, what is the most affordable?
See, with all the basic features, like you have in mobile, if you take 7,000, 8,000 rupees mobile, that will have all the basic features. That when it comes to hearing aid, if you take a hearing aid of 12,000, 13,000 rupees, that will have almost. Rest of the things are all fascinating things, which if you can afford it, if it is there, it's like own voice processing. If you can afford that starts with 30,000. So that is there, that is good. But without that also it will work. You have to do a little bit of programming. So 12 to 13,000 you get.
Thank you for your valuable insights into problems of hearing loss, advancements in hearing aids, signal processing techniques in hearing aids, how to train artificial neural networks for hearing aids, and at the last, gaps in signal processing. Now, I would like to request Dr. Chandrasekhar M. Padvi, Professor and Head of Department of Electronics and Communication Engineering, to hand over the